Today, let's only think about the LPS to TLR binding. We will show that amount of extragenous LPS from outside the cell will be roughly proportional to the activation of TLR, such that this step is actually not crucial. We can start modeling this with this simple equation that we use in chemistry. So we can suppose that there's an external LPS from outside the cell, and there will be TLR on the surface of T cell that are still not activated, still not bound with LPS. And if they bind, there will be a forward rate. With this forward rate, it will become an active TLR. And from some active TLR, there will be reverse rate that brings back to the dissociation of the active TLR into inactive TLR. So this is a forward rate. This is the reverse phase. Now, one thing you have to know is that just like the SI model, to become an active TLR, LPS and inactive TLR should bind together. They should be in the same place. So we'll have this multiplication of the concentrations using the probability concept. That means that the forward rate is not just a rate. Usually a rate is some unit per time. But before moving on to this active TLR compartment, there will be an LPS multiplied by TLR concentration. So we have this concentration squared. And then after it moves to the active TLR compartment, we only have concentration without the squared. So we can guess that this F is actually a unit that somehow hides a concentration somewhere to compensate for the non-squared concentration in the active TLR compartment. So we can guess that F will be, in fact, not just a unit of time, 1/time, but it also is unit of concentration as well. This way, the square can be removed and the unit will become consistent. On the other hand, the reverse rate is just a unit of time, 1/time. And in fact, we'll learn that R over F is the dissociation constant, which has a unit of concentration. And it makes sense because we already said that R will have a unit of 1/time. And F will have a unit of 1/time multiplied by 1/concentration. So these two can be cancelled out. And what happens is only 1/(1) concentration which will be just concentration. So the left-hand side and right-hand side are consistent. How we get to this? We use the same method that we have already used. So if you consider the rate of change on the side of active TLR, as we have discussed previously, movement from the left compartment to right compartment requires meeting of those two molecules. So we consider them in multiplication and multiply by the rate. It will become the rate of change for active TLR. But then what's in the active TLR compartment will move back to the left compartment with the rate R. So we can consider exactly the same thing. Now we consider the steady state. The steady state is when there's no change in the rate. Once again, if we have talked about the differential change of active TLR per time, that will become 0 now. And there will be no further change, and it will not move at all. So that's called the steady state. So let's consider this steady state condition. And what we can do is to move this part to the left-hand side. Then we can arrive at this. And simply then move the forward rate to the left-hand side and move the active TLR to the right-hand side. And after the rearrangement, we have this, which is R over F equals concentration of LPS multiplied by concentration of inactive TLR divided by active TLR concentration. And that, as you know, is a definition for the dissociation constant. The reason why this is called dissociation is because this is a ratio of the reverse rate over the forward rate. As you know, the reverse rate is about dissociation. An important reminder is that KD is in the unit of concentration. Which means that if you talk about the rate, you normally imagine speed, the rate of change, which can be speedy, which can be slow. Much of this information is cancelled out because we are thinking about the ratio between the two. So for example, suppose this happens, the forward rate happens at the rate of 10 nanosecond per molecule. Some kind of molecular unit can be molar if we are thinking about the concentration. We are thinking actually about the concentration, it should be molar. Like that. But then the reverse rate can be much slower, so it can happen in the order of 1 over 1 microsecond. And we have a big difference between the two. So 1 over 1 microsecond over 1 over 10 nanosecond multiplied by the molar will be one over 10 to the power of minus 6 second over 1 over 10 multiplied by 10 to the power of minus 9 second, which will be 1 over 10 to the minus 6 over 1 over 10 to the minus 8 seconds. It so turns out that 1 over 10 to the minus 6 is actually 100 times longer time scale. So this can be visualized by multiplying 10 to the power 2 on both sides. These can be cancelled out. Then you will have m multiplied by 10 to the power 2. So this is what you get at the end of the day. All the underlying differences that represent the actual time scale are cancelled out. So we are only showing the relative differences. Because of that, the dissociation constant doesn't really tell you just how fast this interaction happens, which can become a very important factor to consider, as you can see in the following discussion. But nonetheless, this dissociation constant, this relative rate, R over F, can still be very important. Now we get to think about the practical terms. The binding affinity, or the dissociation constant of the LPS to TLR, is actually just in the nanomolar range. What does it mean? Well, we'll see the answer in the following discussion. First thing we can remember is that the forward rate is much faster than the reverse rate. In fact, it roughly means that forward rate is faster by 10 to the power of 9 times